So, vectors. These guys have been known to give a few folks problems in Lightwave and in the node editor, and it's generally just because they're misunderstood more than the fact that they're difficult in any kind of way. First of all, and this goes back to what I was saying in the video about numbers in general and how we use those to describe things, vectors are a certain type of thing, and even though they themselves get described as a series of numbers, they really are their own sort of object in a way. The reason a lot of folks get confused with vectors is because they don't see the immediate natural connect to a lot of things in the normal world, at least not the way that vectors are described a lot of the time. But the truth is that they're very natural and we use them all the time. For instance, the phrase that away is a vector. Under the sofa is a vector. If I tell you to go straight down this street to the lamppost, then turn right and carry on straight again, I've given you a whole bunch of vectors, 2 translational, 1 rotational, and a location point in space. And that, essentially, is what we do with vectors in Lightwave. That's what we're saying. That's what we're telling the network to do. Is something pointing this away? Make something rotate that amount. Tell me the direction that is facing, and so on. Vectors do come in different flavours as well, which you do need to understand to make sure that you're giving the right kind of instruction or querying the correct kind of property. Now here, of course, is how you commonly see vectors drawn or described. Little vector as an arrow on some sort of grid. And you'll often hear people say, a vector is just a direction, it's just a this, that and the other, and it is, but it's sort of lots of other things that you can sort of derive from this as well. Such as, a vector can be thought of as just a location in space with a particular, x coordinate and a particular y coordinate that it has. No need for any arrow or anything, it's just a point, a vertex in space with a position. So a vector can be a specific location, a position. However, since any graph that we're going to be putting vectors on always has to have an origin somewhere, then you can always trace this line from the origin to that point on the graph. And of course there's our arrow. And in this way, the vector can be thought of as pointing in a certain direction in space. So it's no longer a location, it's a direction. And if thought of as a direction, then every point, of course, along this line would be describing the same vector. In terms of position, these are all different vectors, but in terms of direction, they're all the same vector. And the difference comes when you come to use a vector somewhere in your node network. Because if I'm entering values and seeking to describe or to query a direction, then it doesn't matter which of these, point coordinate values I enter. It's always effectively the same result. If, however, I'm trying to instruct or ask about a specific location, then I have to make sure that, the values are correct. Now there's something else going on with our vector here as well, is that of course we can look along its length and discover that, well, in fact, it has a length. Every vector will of course have a length to it, because if you've got your vector going off in space like this, then by simply drawing down to make a right angle with any of the other axes, produces a right-angled triangle, from which of course you can use good old Pythagoras to find the length of this side. So since it's kind of like a side, it has a length depending on, of course, where this position is. And so that can be measured or instructed as well. So you can take a vector that describes a specific point in space, and you can use that as a direction instead, whilst instructing it to have a certain length. And this is how you begin playing with the vectors, taking one from somewhere, modifying it, plugging it into something else. This whole length thing comes in important in other respects as well, most specifically when dealing with directions, which way things are pointing. In that case, the vector used tends to be what is called a unit vector, meaning all we're really caring about is the direction, and the length is just taken to be 1. Of course, it should also be remembered that any vector with any length can also have a unit vector associated with it, or rather it can contain sort of a hidden unit vector vector, if you will, and so sometimes this can be used instead. This is why things like bump maps and normal maps are vector inputs. In the case of a bump map, we actually ditch the direction pretty much altogether and only care about the length, how far up or down. But it still has x, y and z components to it. A normal map basically does the same thing, but the scale of the vector for each x, y and z is encoded separately in the RGB channels. So let's take a look back in Lightwave at some vector things. So here I've got a vector of 111 on all axis. Plugging in there, of course, it reads out 111. And in this case, this really could be, a direction or a position or whatnot that I was describing in this way. Let's take a quick little look at this length that I was explaining and the good old unit vector. You can turn any vector into a unit vector by using the normalize node. This basically takes any vector and scales it down to have a length of 1. You notice if I plug in, my 111 vector has become 0.58, 0.58, 0.58, which is how far out a point would be on x, y and z, and the line from it back to the origin measures 1. And you notice that it doesn't now matter what I put in here. As long as these three are equal, or the proportion between them, whatever, remains equal, then you always get the same output from your normalize node. Where you will or won't use it will vary depending on the kind of information you're trying to get or the end node that you're trying to supply. For instance, let's say that we were looking at this ball here. The normals of each polygon represent vectors, but they just, go off into infinity. So these are all treated as unit vectors. They have no length associated with them. And of course they are directional vectors. The vertices, on the other hand, are of course all positions in space, relative to the origin, and as such there will be a given length between each point and the origin. But there are also other ways we can view our vectors as well, and that's in terms of angles, away from coordinate planes. This of course can be done on all axes, and of course, like everything else that starts to make this shape, gives us ways to examine it as though it were a triangle, bring in sine and cosine, and essentially treat it rotationally. One thing that does catch folk, and it's kind of easy to see why because it's a little bit funny to picture in your head, is what happens when you have multiple axes who turn through 90 degrees, or of course more. If the x-axis has turned 90 degrees and the y-axis has turned 90 degrees, the line's gone up 90 this way, down 90 this way, which way is it pointing? The result is down the middle, so effectively 1, 1 on each of the axes. And of course we see this nice and plainly here when we enter 90, 90, 90. All three are exactly the same, so the vector is pointing directly out equally between the three axes. And if we go back to our normalize and we normalize the 90, 90, 90 rotation, you see we've got the 0.58 result again. So 90, 90, 90 here, in direction terms, is the same as 1, 1, 1 here. Or 10, 10, 10 here, because we're talking about direction. Okay, so we've been through a fair few of the basics now, and we've explained vectors in these various ways, how they can be taken as one thing or another thing, how they're all kind of the same thing at the same time. And it's all been very nice and sort of light and fluffy. In spite of that, there is a way to working with them. They do have a logic and a mechanic to them. And that's the tricky bit to learn, of course, if you're new to it all, is how you actually go pulling them in the right way. For instance, here I've got a camera and a null object. Let's get a good old item info here for the null. And we have its position, which is a vector. We want to target the camera to it. So we might think, since it can describe a direction, I can just plug it straight into rotation, right? Wrong. It all goes a bit mental, unfortunately. And we see that what we get is absolutely nothing like the targeting that we would hope to have. Here's the first trick. It's the standard logic of the node editor. Follow the numbers. I've got here a position vector, an XYZ value. Here I've got a rotation input, which is also an XYZ, but really it's a heading pitch bank in that order. So what is happening is the X position is driving the heading, the Y position drives the pitch, and the Z position drives the bank. It's effectively a totally useless constraint. So, what we see is that when working with vectors, we are still following the numbers just like anywhere else in the node editor. Despite all of my lovely fluffy hippie talk about how they're just all of these pointing off in directions and locations and they can be treated in any which way, Lightwave can't figure out exactly what your intention is, so it just does its direct map. It's got no way of knowing that you want this to be treated as a rotational direction for this. Not to mention, of course, getting the rotation order correct. We see, for instance, that if I get a split vector node here and a make vector node, and I cross the x and y and keep the z to make the rotation order correction and plug that in, when we move on x, the camera is indeed pivoting around the x-axis, which is pitch. And when we move on y, it is rotating around the y-axis, which is heading. But this still hasn't given us our targeting behaviour. It's still just another useless constraint. What this problem introduces us to is some of the tools that we have for working with vectors, and how these translate into the nice fluffy ways of thinking about vectors. And it also introduces yet another way of speaking about them, another kind of terminology. And that is these things: right, up, and forward. The right, up, and forward represent what's known as a rotation matrix. You also have the world right, up, and forward, this being the rotation matrix relative to the world, or the inverse of the local rotation matrix. The terms are pretty simple and represented for us in the viewport. The vector right is the little red arrow, the x, up is y, and forward z. So we can see these vectors right there. As I said, they represent a rotation matrix. What that means is if we rotate our null somehow, bring up the move tool in local axis mode, we see that of course these handles have realigned. The way that these are pointing, the values assigned to these vectors, is now what is popping out of the item info node for right, up, and forwards. If we hook this up to an input spy here from the up vector, we can see that the coordinate is 0, 1, 0, so 1 in y, pointing straight up in y. If we switch to the side view here and rotate it on pitch, of course switch back, we can see that our y vector has now turned into the z axis, and hitting update here we now have a yz coordinate. If I take the world up and plug that in, we see essentially that it is the inverse. If we had an up input here, then essentially plugging this value in would cause that to rotate back to its previous orientation. Of course we can see this with the other vectors as well. If we look at forward, we see of course that that has come down negatively on the y. And this is what our rotation matrix is. Here's the deal. We've got an x-axis, right? And that's got its vector coordinates. We've got a y-axis, and that's got its coordinates, and we've got a z-axis. And what a surprise, that also has its. This here is what folks call a matrix. Isn't it lovely? And it's basically a fancy way of describing something like, in this case, a rotation with 9 separate coordinates, which is handy. First thing you'll need to know is a little bit of nomenclature if you're not up on it. Basically, it's like Sudoku. You have rows and you have columns, or like an Excel spreadsheet, really. If you've ever done Excel, this will be fine. Now, if you do go on to do further reading, what you shall discover is that there's two ways that people like to represent full three-dimensional matrices like these, or 3x3s as they call them. 3x3, which is what we're concerned with in Lightwave. There's the more common favourite of the math folk, which is to write things as they call them in column vectors, like that. And so the matrix becomes made up of 3 column vectors like this. Look at me, V2 and 3, what a wonderful choice of axis naming. Good thing I didn't make Lightwave. The more common way that you'll see it done in computer graphics stuff, though, is this way, with row vectors. Now, much is often said, of course, about how things are presented in interfaces and what's, helpful or intuitive or easy to get along with. And it's not too hard, really. I mean, if you're getting along with the box down in the corner of Lightwave that's been there since forever, then you can pretty much get along with this. These two different types of writing don't make any difference apart from in any of the stuff that you may read up on with other vector stuff. You might encounter either method. For Lightwave's purposes, it uses row vectors, essentially right, up, and forward. There is one semi-hilarious thing in Lightwave, which is well seen in the Transform 2 node here, where the matrix is entered just as one big long column. Talk about unintuitive for artists, this isn't even intuitive for programming folk, I don't think. But there you go. Lightwave's always good fun. So, knowing that stuff, let's get back to our problem. Now obviously some of these nodes are discussed in the nodes collection videos, so don't worry too much about not knowing the nodes themselves at this stage. The basic mechanic for what we're doing should still be obvious. If we search out matrix here, or matra in my case, we can see the node tools that we've got, including HPB matrix and matrix HPB. These are basically opposites of the same thing. This is the one that we want here, the matrix to HPB. This will take a 3x3 matrix in positional coordinates and output an appropriate heading pitch back value, with the rotation order already set for us, as it should be. So if you're thinking, okay, what do I actually want from the null? What info do I want from it? Do I want its forward? Is that what I want? We give it a try. Plug it in. Not quite right. But look what we've got. The camera is matching on pitch. We've got yet another constraint. This time, it's a reasonably useful one. Although this is a little convoluted, it's achievable in other ways. Basically, it's looking at this z-axis, which way it is pointing, and rotating that to match. That's not what we want. We want the position of this null in the world axis here. Both the null and the camera are, of course, just scene children, so they're both in the same reference space. So what we actually want is the null's position, which in this case, of course, is the same as its world position, because that is the direction that we want to become the forwards axis of the camera. Here's the camera with its local axis, and there's its z, which is what we're instructing here, which way to align the forward. And so there it is. If we move our null around, our camera will now target it. Of course, it works in the negative space as well, and there it is. Good as it seems, we do have a problem. If I go moving my camera, we see that it doesn't target the null. It rotates to target as though it were at 0, 0, 0. The reason for this, of course, the position value that we have coming here from the null is its position relative to the origin. That's the vector that we're getting, and that's the vector that it's rotating to. We need to try and find this vector here. The simple way of doing this, because in this instance they are in the same space and have the same origin point, is to simply subtract away the movement of the camera. Take this extra movement and chop it off. We get another item info, this time of the camera, along with the subtract null. Take A, the null position, B, the camera position, pump that into the forward. And now our camera targets the null, whichever of the two is moved. So there we go, another way of thinking about describing vectors, at least in terms of rotation, or principally in terms of rotation for our purposes here, and how we actually go about instructing a conversion from one type of vector interpretation into another type of vector interpretation. I could of course have another null, pipe its position to the up, and of course the y-axis of the camera would align to that, which would be the bank rotation. That would be a pole vector, or an up vector as it gets referred to. Speaking of such things, here's a handy incident little tip for in the node editor here, especially the nodal motion. Even though my targeting is only controlling the heading and pitch, because that's all it needs to achieve the forward vector, I've got no control over my bank here by keyframing, because it is being forcibly driven by the nodes. And since there are no vector inputs, it's just being forced to 0. In case you're thinking, how might I mix that in? Here's a way for you. You take a couple of split vector nodes, take the heading pitch bank coming out of here, take the heading pitch bank coming out of here, take the X and Y from this whole setup, which is of course the heading and pitch, and then take the bank from that. This should just be the keyframed value, right? And there you have it. Now, we could go further, start building in rotational limits with, of course, clamp nodes, remap with gradients, so on and so forth. And whilst this is a fun and interesting little node setup, it does actually have a practical application here. We might normally think not to need to use it too much, as we of course have pre-built target and pole item settings in our motion options, which of course work together with the IK and other systems. Remember, however, that nodal motion is a motion modifier, and so has a different place in the evaluation order. As was pointed out, if you double-click the nodal motion node, it has an after IK switch. So here is a target item set up that you can have occur explicitly either before IK evaluations or after IK evaluations, which is a distinction you cannot make with the built-in target and pole item controls. So with just a handful of simple nodes, we've been easily able to give ourselves access to a familiar type of control in a whole new way, which we previously could not have. And it goes further, of course, because let's not forget that you've also got one of DP's plugins, which is the node channel filter here. Of course, channel filters, again, taking place at a different point in the evaluation order. You could set up the motion control via that node editor instead. So there we go. With a few simple nodes, we've got a nice, handy way to access a tool that we're familiar with in a whole new way. But guess what, of course, we can take it even further still, because we're in Nodal. So we can take something like this and pop it into a texture editor instead. Here I've used the heading pitch bank to drive the rotation of a procedural texture. And if we hit the VPR, we can see the result. There's a texture, and as I move the null, we can see that the texture rotates around. It does, however, seem to be going backwards, which is unusual. Obviously there's a different transform here on this, but we can fix that nice and easily with a vector multiply, I do believe. -1 on all axis will do. To be honest, I probably only need it on the heading, but there you go. And our texture now targets the null, and of course still respects the position of the actual plane the texture is on, had I not used that, of course. And because it's nodal, we can of course keep going and welcome a few more vectors here. In this case, the spot info node, so I'm getting the positional vector of every spot on this surface. In this case, just in object coordinates is fine. I could be using world. An item info, referencing a new null, which is here. Vector distance node, that takes two vectors and gives the distance between as a scalar. Obviously, very close is 0. So I've remapped that through a gradient here, where 0 is a alpha of 100 and 1, so 1 meter, is an alpha of 0. I can take that alpha into a multiply node, multiplying of course the result that we already have here from the rotation setup, plug that into the rotation, and what we now see is that it only rotates around that null. I can shove this around to move the distortion and displacement, the rotation. Animate these two things together, throw other things into the mix, you can get some quite interesting texture animation going on. It's kind of like a way to rig your textures. And so there you go, that pretty much wraps up all of the fundamental basics that you need to know about vectors to start using them in Lightwave, and an introduction to some of the methods of looking them up, converting them, and using them to drive different things